Welcome back. So this is now a lecture again on Ricci flow, and we start by deriving the evolution equations for curvature, assuming for the moment that we already have some solution. So this is about the evolution equations. And suppose g of t is a smooth solution of Ricci flow. So we have ddt of gij equals minus 2rij on some time interval and on some smooth Riemannian manifold. And then the first thing you can compute from this is an evolution of the inverse metric, which is important. Now the time evolution of an inverse metric, just like for real functions, is the square of the inverse with a minus sign. So we take GIL G upper jk times the derivative of the metric, which we insert from here, so we end up with plus 2r with both indices up. And a similar easy computation is the change in the volume. So if you take the volume form to be d mu, then in some local coordinate system this would be ddt of the square root of the determinant of the metric gij times dx, which we can compute as 1 over 2 square root of the determinant of g times the derivative of the determinant. This gives us the cofactor matrix determinant of g times g upper ij times ddt of the metric. General formula for the evolution of a determinant, and this in turn gives us the square root of the determinant reproduces the metric volume form, and here was a dx missing, so we get g upper ij times ddt of gij times d mu, and this, if we use Ricci flow, we get the trace, and the 1/2 cancels the 2, so we get minus the scalar curvature times d mu. So in particular, we get, if the manifold is compact, we get that ddt of the volume of the manifold Mng is equal to minus the integral over Mn of the scalar curvature times dEg. So if the scalar curvature is non-negative, then the total volume of the manifold is decreasing. Now in the next step, we want to compute the evolution equations for the curvature quantities, because the curvature determines the shape of the manifold, and for that we start with the evolution equation of the Christopher-symbols. So, as you know, the Christoffel symbols, this is number 3, are given by (1/2) g upper il, is the coordinate derivatives ddxj g l k plus ddxk times g lj minus ddxl of gjk. And to compute the derivative, we're now using a trick which is also very useful in many other situations, also later in the evolution of the curvature tensor itself. We use the fact that we can, at any given point, in any given time, use normal coordinates at the point and time where we do the computation. Of course, you have to be very careful because it will only be valid at that point and that moment in time that we have normal coordinates. But if we use that cleverly, then we can create the evolution equation much more easily because we avoid a lot of terms. And important in doing it is noticing that while the Christoffel symbols themselves are not tensor, any difference of two Christoffel symbols, and certainly the derivative of a Christoffel symbol, is a tensor. So whatever we compute in the end will be valid in any coordinate system. So it is allowed that we do our computation with this trick using the normal coordinate system at a given particular point where we do the computation. Right? Left-hand side is a tensor, so the right-hand side will be a tensor. So we do the computation in a normal coordinate system at a point. At such a normal coordinate system, these derivatives are, of course, all zero. So we don't have to differentiate the first term. In this case, it will create zero. So we only have to differentiate these terms here. We can commute the ddt with the ddxi's, so we can immediately insert the Ricci curvature here. So doing this, we get 1/2 g upper IL times, and now inserting here the Ricci curvature and noticing that we are at a point where the Christoffel symbols vanish, we can also replace the coordinate derivative now by a covariant derivative. So this becomes gradient j of minus 2RLK plus gradient k of minus 2RLJ and minus gradient L of minus 2RJK, such that this whole computation reduces to minus gradient J of Ricci IK and minus gradient K of Ricci IJ and plus gradient I of Ricci JK. And this is ddt of gamma I jk. And here you have a tensor identity. You have a tensor on the right-hand side and you have a tensor on the left-hand side. So now that we've done this computation in one coordinate system, it has to be true in any coordinate system. And if you try to do this in any coordinate system, it'll be a much bigger mess. Okay, this gives us the evolution equation of the Christoffel symbols. And now we can use our formula for the Riemann tensor using a similar trick to compute the evolution equation of the Riemann tensor. Evolution of the Riemann tensor. Well, the formula that we had for the Riemann tensor involved Rij KL, well, sorry, RHIJL was equal to the derivative of gamma HJK minus the derivative dxj of gamma HIK, and then there was some product of Christoffel symbols minus another product of Christoffel symbols. When we now compute ddt, we can, in the coordinate system, in the normal coordinate system where we do the computation, ignore those two terms, because one of them will always be 0. So we have to just concentrate in that coordinate system on those terms. So computing ddt of RHIJL will come down to just computing this. And now computing here, again we can pull the ddt past the ddxi, and then, because we are normal coordinates, replace the coordinate derivative backwards with a covariant derivative. So we will get gradient I of ddt of the Christoffel symbols HJK minus gradient J of ddt of the Christoffel symbols gamma HIK. So with this simple trick, we know this is a tensor, this is the tensor. We certainly get this identity actually for any evolution equation, not just for Ricci flow. Now, inserting the Ricci flow in here and collecting terms, what we end up with is the following. We get gradient I, gradient H of RJK minus gradient I, gradient K of RHJ, and minus gradient J, gradient H RIK, and plus gradient J, gradient H, gradient K, RHI. These are the second derivative terms, and then there's two more terms. There is a difference between gradient J, gradient I of RHK and gradient I, gradient J of RHK. So this term here is a commutation of two indices, so we can replace this term by a curvature term. On the other hand, we also want to have that ddt, we want all the indices down, so what we really want is ddt of Rij which is, of course, ddt of the product where we have G H K times R H I J L. So to get this, we also have to take into account the evolution of GHK, so this gives us minus 2 Ricci HK times RHIJL, and in addition GHK times the time derivative that we just computed of RHIJL. So we have this term, and for this we can insert the formula up here, and this will lead to the following. putting these two formulas together, we end up with ddt of r I j k l is equal to gradient I gradient k r j l minus gradient I gradient L R J K minus gradient J gradient K R I L plus gradient J gradient L R I K. And then when you collect the commutator terms, you get two commutator terms because there's two indices involved from the previous line, and one term that came from the derivative of the metric. If you collect them, you end up with R I J M L times Ricci M K, and another term which is R I J M K times Ricci M L. I hope I got it right. You have to be careful here, of course, not to make a mistake in commuting two of these indices, because it will introduce a wrong minus sign. I think the formulas are right. And now this is a form of the second derivatives of curvature, which is not really what we want. We want to have sort of a nice operator acting on the Riemann curvature tensor. Now what you see here is we have second derivatives of the trace. What we really would like to see is a Laplacian. We would like to see the trace of the second derivatives rather than the second derivatives of the trace. So we have to replace the second derivatives of the trace of the Riemann tensor by the trace of the second derivatives of the Riemann tensor. This is called a commutator identity, and this commutator identity is the intrinsic analog of the Simon's identity in extrinsic geometry. Analog of Simon's identity in extrinsic geometry. And this is the following lemma, which I want to leave as an exercise. You set, for notational purposes, you set Bijkl using the notation that Hamilton introduced. This is a square term in the curvature. Take the first index up, then I, then the second index also up as a summation index, J, times the Riemann tensor R, P, K, Q, L, and sum over P and Q as usual. And then you have the following identity, the Laplacian of Rijkl. So the trace of the second derivatives is equal to the term exactly that is up here, gradient I, gradient K, Rjl, minus gradient I, gradient L, K, J, minus gradient K, gradient J, RIL, plus gradient J, gradient L, RIK. And the commutator curvature terms that arise from this are minus 2 Bijkl minus Bijkl j lk minus bi l jk plus bik jl. So these are 4 quadratic terms in the curvature. And then there is 2 more. There is plus r I q Ricci tensor times r q j k l plus r j q times Riemann r I q k l. It's a magical identity which shows you that Ricci flow is rather special, because we can now replace this whole sum of terms in the second derivatives of Ricci by just the Laplacian of the Riemann tensor plus some quadratic terms in the curvature. And if we collect it all together, we end up with the following main theorem. Under Ricci flow, the Riemann tensor satisfies ddt of Rijkl is equal to the Laplacian of Rijkl. This is, of course, the Laplace-Beltrami operator with respect to the metric Gij, which itself is changing in time. So we get the Laplacian plus 2 times these quadratic terms, bijkl minus bijlk minus biljk plus bikjl, and then we get these terms here, minus riq rqjkl plus rjq riqkl plus rkq rijql plus rlq rijkq. This is it. This is the main theorem that tells us how the Riemann tensor evolves under Ricci flow. And let me again point out how special this is. From a certain point of view, you can view this as a reaction diffusion system. But a very special one. Special in the sense that, again, you have the same diffusion speed in all the components. You have exactly for all the components the same diffusion. So isotropic diffusion. And not just isotropic in all directions of space, but in all the directions of the curvature components. And it's diagonal. So the time derivative at each point of a component is just given by the Laplacian on that particular component. So it's not mixing the second derivatives of all the components of the Riemann tensor, which would be a much more general system, which often comes up in other circumstances. But here, the Ricci flow, it is sort of in the nicest possible way. You couldn't have it any nicer than this. So in a sense, it's diagonal. And of course, it also has a scaling invariant. If you think of the Laplacian being like two derivatives, which is the same scaling as the curvature, then this of course perfectly fits the quadratic terms in the curvature on the right hand side. Comparison again to mean curvature flow, compared to mean curvature flow, where you had ddt of the position, remember, is equal to the mean curvature vector for a hypersurface or a submanifold in Euclidean space. In that case, it turns out that ddt of the second fundamental form has a very similar structure. So Laplacian of the second fundamental form, and let me erase one index here to make it even easier. So it's a ddt of the second fundamental form, or the Weingarten map, and this is just the square of the second fundamental form. That's this. So we have a similar structure. It's also sort of this isotropy in the diffusion. It's also diagonal in the leading order term. And then this cubic term here, of course, is the same scaling is there. It's cubic, but that comes from the fact that the second fundamental form scales like 1 on distance rather than 1 on distance squared. So the cubic term is just right, again, to make the scaling right. So it's very similar to Ricci flow, but it has a different algebraic structure. So the main difference between the two is the different algebraic structure in the reaction term. Okay. Once we have this, we can now record immediate consequences from this, like the evolution of the Ricci curvature and the evolution of the scalar curvature. Let's do that. Now for the evolution of Ricci curvature, we just take ddt of Rik, which is ddt of the trace of the Riemann tensor. So we get ddt of the inverse metric, which we computed before. This was 2 times Rjl times Rijkl, sum over L, plus ddt plus gjl, the trace of what we just computed. And when you do the computation, just put the two things together and do the obvious contractions, you end up with the leading term coming from here. Turns out the Laplacian of the trace, which is Laplacian of Ricci. And then the commutator terms turn out to be 2 times Rijkl times Rjl, this is this one, and the other one that comes in is a term which looks like minus Rilrlk, so it's just the square of the Ricci tensor. And once you have that, you immediately get the evolution of the scalar curvature by taking the trace once more. So we get ddt of R is equal to Laplacian of R, well, let's be slow, this is ddt of gik times rik. So we get from here a 2 times rik times rik and plus the trace of this equation, which is the Laplacian of R, and the trace taken here is plus 2 rik or JL, which is of course the same. And then here, taking the trace of this is minus 2 RILRLI. And of course, these terms here and here are all the same. So 2 of them cancel. So we end up with ddt of the scalar curvature is equal to the Laplacian of the scalar curvature plus 2 times the Ricci tensor squared. So yes, these are the 2 formulae to remember. And notice that in the 2-dimensional case, when we are on a Riemann surface, then of course we only need this formula, because R is 2 times the Gauss curvature, and Ricci squared again is just twice the square of the Gauss curvature, and therefore the equation is just ddt of Gauss curvature is Laplacian of Gauss curvature plus Gauss curvature squared. But in the 3-dimensional case, we need this, but we don't need the full Riemann tensor, because remember, in the 3-dimensional case, the full Riemann tensor can be computed from the Ricci tensor. So in the 3-dimensional case, we can compute this term in terms of the Ricci tensor, and therefore we have a formula that gives us the complete evolution for the 3-dimensional curvature just in terms of this one formula where we have inserted the formula that we had previously for the Ricci curvature here. Okay, so let me make one comment about these many curvature terms. It turns out that some of these curvature terms are only there because as we change the metric, the length of the base vectors in our coordinate system are changing. So it's sort of not really, these terms are not really reflecting the change in the curvature, they are reflecting the change of the scale in which we measure the curvature. And it becomes slightly more clear if we eliminate this effect, and this is a useful trick that I want to show you. This is the formula that we derived for the Riemann tensor, and the terms that I would like to remove are these ones here. So the claim is that these terms are due to the change of length of our vectors ddxi in time. And they can be removed if we change our coordinate system in time so as to remain orthonormal, for example. And then we can just completely eliminate these terms, and we just have a slightly nicer equation, which is given by the first line in this formula. This was first carried out by Richard Hamilton, who got the idea from Karen Uhlenbeck, so he calls it the Uhlenbeck trick. And the idea is to, given an initial orthonormal frame on Mn with the initial matrix G0, say EI, I between 1 and n, so we have a G of EI Ej equals delta Ij, then the idea is to solve a system of ODEs where you change ddt of the kth coordinate of the ith vector in time at a point in time by solving R. Let me just make sure I got this right with the indices. You write R K M, so this is the Ricci tensor with one index raised, RKM times the nth coordinate of ER T. Just solve this system of equations for each EI, and then you of course get that in this that this new inner product of EI of T and EJ of T, which is GKL times EIK times EJK, EJL, and you get ddt of this and you compute from here, you get the Ricci flow, so you get RKL and times EI K EJ L, but from here you insert the formula, so you get GKL times R M K E M I times EJL, and then you get from this term here plus GKL times EI K times R M L times E M J. And if you stare at the indices, you see that these two terms just completely cancel out, exactly like these terms here, just different summation indices. And because this index gets lowered, so this is R lower Km, EMJ, EJ, and so on, and this just cancels completely out. So this evolution system makes sure that the EI of T's remain orthonormal. So now you are in a frame that's evolving to remain orthonormal along Ricci flow, and then when you compute what kind of effect it has on the evolution equation, then in this frame, then in this new frame, which is now changing in time, EI of T, we get that ddt of R, let's call it tilde, IJKL, is equal to Laplacian of R tilde, IJKL, plus 2, and then you get the B's and nothing else. And when you do this in the case of the Ricci curvature, it turns out that the last term in the Ricci curvature equation goes away, so you get d r tilde ij is equal to Laplacian r tilde ij, and you just have the extra term plus 2 times r tilde kl r tilde I k j l. And by the way, you can achieve, the last term goes away. As long as you just have a symmetric 2 tensor, you can also achieve the same effect in the original coordinate system by just raising one index. So this is equivalent to saying in the original coordinate system, without the tilde, that ddt of r upper I low j is equal to Laplacian of r upper ij I lower j plus 2 times r kl Riemann 1 index raised r I k j l. And it's an interesting exercise to do the same thing for the evolution of the second fundamental form in mean curvature flow. Okay, let me now just finish by recording one corollary that we get immediately from the evolution of the scalar curvature, where we can immediately apply the maximum principle to make some interesting conclusions about solutions of Ricci flow already. So the evolution of the scalar curvature is still on the board. Let me just keep it here. Bottom. So, because this term is positive, you can immediately draw conclusions, because in particular this means that the infimum, just by the parabolic maximum principle, the weak parabolic maximum principle, is that the infimum of the scalar curvature will never be able to decrease on a compact manifold. So let's record as a corollary. First conclusion, let's assume that the manifold is compact. Assume that and it's compact, so we don't have to worry about infinity with the maximum principle. Then first of all, any lower bound on the scalar curvature R is preserved. This is just the weak maximum principle. In particular, if interesting cases, if the scalar curvature is non-negative, then it remains non-negative. In particular, if scalar curvature greater or equal to 0 at t equals 0, this remains. But we can also use the Hopf maximum principle, the strong maximum principle for scalar parabolic equations, which tells us that the only way that the scalar curvature is not turning positive, strictly positive, is that it remains identically 0 and was in fact identically 0 at t equals 0. So we also have that the scalar curvature at P is strictly bigger than 0 for all P in Mn and all T strictly bigger than 0 unless R is identically equal to 0 on Mn, and in fact the right hand side is identically 0. So Ricci is identically 0 at T equals 0. So this is the first rigidity statement that we get from the Ricci flow. If you have a manifold with non-negative scalar curvature, either you can immediately deform it with Ricci flow, the metric, into a metric of strictly positive scalar curvature, or the manifold had vanishing Ricci curvature already in the first instance. Okay. This there will be many more such rigidity statements in the future for Ricci flow. They are crucial for understanding the flow. So now we can make more quantitative statements because we can relate this positive term back to the scalar curvature. So recall that the Ricci curvature squared is always bigger than 1 on n times the scalar curvature squared. So we get a differential inequality. We get ddt of r is bigger always than the Laplacian of r plus 2 over n times the scalar curvature squared. And now the maximum principle allows us to make a comparison to the ODE. So this means we can compare by the maximum principle to solutions of ddt phi equals 2 over n phi squared. And these immediately give us the following statement. If the scalar curvature initially is bigger than some positive constant, C0, then we can compare to this solution of this ODE starting with the value C0. And therefore we get that the minimum of the scalar curvature at time t has to be bigger than the solution of this ODE, and this happens to be C0 divided by, now I have to check the constants right, so this is 1 minus 2 C0 over n times t. In particular, we see that something has to go wrong at a finite time. So we must have that the maximal time of existence on such a manifold for the Ricci flow, for a smooth Ricci flow, must be less than n over 2 C0, which is the right scaling. Time should scale like distance squared, and 1 over curvature is exactly like distance squared. So we have a first singularity criterion. If on the initial compact manifold the scalar curvature is uniformly positive, then the solution of Ricci flow can exist at most for a finite time. And of course you see from here also equality holds exactly in the case where we have constant scalar curvature, which was our example for Einstein manifolds. And the fourth statement that we get immediately is, of course, if the C0 happens to be negative. So if scalar curvature is bigger than C0, but C0 is a negative number, then with the same argument, we see that the minimum of the scalar curvature is slowly improving, and we get minus, the corresponding solution is then C0 over 1 plus 2C0 over n times t. So as t gets larger and larger, even as t tends to infinity, this will get a smaller and smaller negative number, so this approaches 0 as t tends to infinity. Of course, in case we have a solution which exists all the way to infinity, which need not be the case in general. So these are the conclusions that one can immediately draw from this simple evolution equation for the scalar curvature. In the next lecture, we look at the short time existence and derive a criterion for the long time existence of the flow. Thank you.